We're going to continue today working in section 12.1, 12.2 on congruence through constructions. And we are on perpendicular bisector. And this will actually help with one of your homework problems as well. So be aware of this when you come back, and come back to this one when you're taking a look at finding the problem exactly is about a midpoint in your homework. So there it is. All right, perpendicular bisector. A perpendicular bisector is a line that is perpendicular to the segment and it bisects it. It's one of those it sounds just like it is kind of things. So the point is the same distance from the two endpoints on the line if and only if it is on the perpendicular bisector. What this is actually telling you is that every point that lies along here is equidistant from the endpoints. Okay, so if I were to find, say, the distance here, that was terrible. Let's try it again. If I were to find the distance here, it'd be the same thing as this distance here. If it's on the perpendicular bisector, it's equidistant from the endpoints. And obviously, whoops, this point right here meets that criterion as well, right? It's on the perpendicular bisector, so it is equidistant from the endpoints. So I believe our next construction is actually, oh, I take it back. It's further down. Let's do a few more definitions before we get there. We are going to construct a perpendicular bisector here in a minute. Okay, isosceles triangles. Catherine and I were just talking about this, actually. Properties of an isosceles triangle. One property is that they have congruent base angles. So you can see that picture right there. It shows a diagram of an isosceles triangle. Two sides are congruent. And whenever that happens, the base angles are automatically congruent. The angle bisector of the angle formed by the two congruent sides is the perpendicular bisector of the base. So that's a really helpful piece of information. If you have isosceles triangles and you cut the angle, that's the non-congruent angle, in half at the top, it automatically cuts the opposite side in half as well. So it creates congruent angles at the top, and it creates a perpendicular to the base at the bottom. All right, an altitude is the perpendicular segment from any vertex of the triangle to the line containing the opposite side of the triangle. A triangle will have three altitudes then, one for each vertex, and they do happen to all intersect in the same point. So every angle, you can drop a perpendicular to the other side. And when you do, for all of those angles, you actually cross at the same point in the middle. All right, now we're going to combine some information about triangles and circles together. There's three things on this particular diagram. Sorry, this slide. Circumscribed. Circumscribed is a circle about a triangle where every vertex of the triangle is on the circle. Okay, and it's unique. There's only one of them for every triangle that will do that, one circle. And every vertex of the triangle is a point on the circle. We would call that triangle inscribed, and we would call the circle a circumcircle. Okay, it circumscribes it, it's around it. It's called a circumcircle, and the triangle is inscribed, it's inside of it. And then the circumcenter is the point that's the center of that circle. But the way you actually find it had to do with those perpendicular bisectors on the previous slide. The point where any two perpendicular bisectors of the triangle intersect is the center of the circle. In other words, over here, this picture, that point where they crossed in the middle, I could use that point, and I'll show you how I can finishing that out in a minute. But you can use that point in the center, and I can create a circle with that point as the center that will circumscribe this triangle. And I really don't need all three perpendicular bisectors to do it because they all three intersect in the same point anyway, so two perpendicular bisectors is enough. That's why it only references 2 perpendicular bisectors here, because if I drew the third one, I wouldn't get any more information than I already had. All right, so we're going to do some constructions now. Looks like 3 more. Only 2 more. 2 more constructions. So we're going to construct the perpendicular bisector. It's the one I just mentioned. And then we're going to construct the circle circumscribed about the triangle. That's exactly what we just did all the definitions on, right? So we're going to take a look at how to do each of those back in the other program. Okay, we have one last example in this section. We have a parallelogram. It says, consider a parallelogram along with one of its diagonals. Do you remember what a diagonal is?
A line that crosses through 2 non-consecutive vertices.
Right, and so there are 2 diagonals here, right? Yes? AC is one diagonal. So if I connected A to C, and the other diagonal is AB.
D.
AD. Thank you. Yes, AD. AC and BD.
Yes.
All right. It says that we're going to consider it along with one of the diagonals, so you get to pick which one, just so that we're all drawing the same one. Let's all draw the same one. Not because it matters which one's which, but just so that our pictures, we're not confusing the issue like me saying things over and over again wrong up here, okay? Let's draw in BD, okay? So draw in on your picture. You can use your straight edge, that'd be great. And draw in segment BD. Okay, do you guys have segment BD? Okay, it says use the definition of parallelogram and the angle side angle congruence property for triangles to show that the opposite sides of a parallelogram are congruent. So the directions are really nice because they tell you how you're going to do it, but you're going to show sort of a series of steps as to why this works. We know that we're supposed to get 2 angles and a side between them. Do you see 2 triangles? Do you see the side between them? Yeah, there's a very obvious side that has to be congruent to itself, right? What between these 2 triangles would be the congruent side that it's referencing? DB, the one we just drew, right? So if you'd like to go ahead and reference that, that can be the first part of your, sort of proof. Not that this is a written out formal proof, but we can justify that very easily. So we're going to justify why certain things happen. So we know that DB, or BD if you prefer, and it's a segment, so please put the segment line piece on top of it, is congruent to segment DB. And do you guys remember what it is that I called that last time? Reflexive, very good. Like reflection in a mirror, right? It's called reflexive. All right, so you're 1/3 of the way there because you're supposed to show angle, side, angle, and you've showed the side. Now, in this picture, do you know one of the angles that you expect would be congruent to one another?
Angle ADB and CBD.
Okay, so Brendan thinks these 2 are congruent. Do you agree? Yeah, but we need to justify why that's true. So any thoughts as to why that's true? Let me, before you start talking, let me write down these angles that you just mentioned. ADB congruent to angle CBD. The order of this doesn't much matter except that the angle's center, the vertex, has to be in the same location. So it's not quite as strict of a ordering as in a triangle, but why? Why are those angles congruent?
Alternate interior angles.
For which 2 parallel lines, Brendan?
DC and AD.
Okay, DC is...
I know they're parallel because it's parallel.
Okay, so DC is right here, and AB is right here. I don't think those were the parallel lines you wanted. Yeah. How about this one? Yeah, that's why I wanted to draw them in, is because it's really easy to get them backwards. Do you see how the black transversal line hits those 2 parallel lines that I just created? And the angles that we marked in red are on them. They're between those. So this is the alternate interior pair that we want. So these are alternate interior because AD is parallel to BC.
Why are DA and CB parallel, but DC and BD aren't?
They are parallel. It's just that when I drew those in, those didn't make those angles alternate interior. See these angles right, this right here has to touch the red line and the black line. That's what makes it alternate interior to this one. So we're going to need those other ones for our other angle though.
If it wasn't like if the instructions didn't tell us it was a parallelogram, could we still do this?
No, we need the parallel lines in order to do this. Yes, absolutely. There's another set of angles that are congruent. What are they? I'll switch my colors up.
Would it be like DAB and DCB?
We don't have anything for that one.
You could do the other alternate.
Yeah, we need the other alternate interior ones, these two. Okay, so what do we have? ABD. And C, whoops, BD. And these are alternate interior as well.
Or C to B, CB.
Did I get my angles wrong? Is that what you're telling me?
Yeah. We're doing the blue ones, right?
ABD, CBD. Okay, thank you. Okay, and the reason these are alternate interior is ignore the red lines. Now look at my blue lines. Do you see how the blue angles hit the transversal? That's the diagonal. And they hit the blue lines. That's what it takes to be alternate interior. They have to be trapped between the parallel lines, which these are. They're trapped between the two blue lines, and they're touching the transversal on opposite sides. So this is alternate interior because CD is parallel to AB. Got all my segment sections up there, I think. Okay, we've got angle, side, angle now, right? All right, I need to make this a little bit smaller so we have some space. Thus, triangle. What two triangles are now congruent? I'm going to start with A, D, B. What triangle is congruent to ADB? C, B, D. Did I get them in the right order? I think so. And why? Yeah, it's angle, side, angle. That was our whole goal, was to be able to use angle, side, angle. Now I have congruent triangles, and what do you know about congruent triangles?
The corresponding sides are all.
Yeah, the corresponding parts of congruent triangles are congruent. So the sides that correspond are going to be congruent to one another. Whoops, let me change this other one. So this side is congruent to this side, right? So we have AD congruent to CB, and what's the other pair? AB and DC. And the reason for both of these is because corresponding parts of congruent triangles are congruent. Any questions on that? All right, real quick, before we call it quits for this section. You have a handout about quadrilaterals. So I'm going to keep the audio recording. There's no visual for this, but you have this handout right here that has some wonderful properties of quadrilaterals. You'll notice that one of them we just proved. Parallelogram. Third line down, parallelogram, a quadrilateral in which both pairs of opposite sides are parallel. the following are true over on the right-hand side. Opposite sides are congruent. We just did that, right? We proved that was true. And could we use this exact same argument to show that the opposite angles are congruent?
Yeah.
Of course we could, because we would have the same triangle kind of argument for that, right? We could keep working through some of these. All of these are things that you can prove. That's why it says related theorems on the right-hand side. It means that these are not facts that are just stated with no reasoning behind them. They are actually facts that can be proven. Some of the things you're going to prove in your homework, group work, things like that. Others of them that you won't. So it shows you about a trapezoid, specifically an isosceles trapezoid, parallelogram, which we talked a little bit about some of these, rectangles, kites, rhombus, and squares. So the only quadrilateral on here that we didn't actually specifically talk about before was isosceles trapezoid. The only difference is that it is in fact a trapezoid with two pairs of congruent base angles or congruent sides, if you prefer. Okay? So this particular sheet will help you as you're taking a look at these. Now, here's the kicker. If it tells you that you're going to prove that the opposite sides of a parallelogram are congruent, you can't say, my sheet says they are. You guys with me? This is not a proof of anything. These are some general facts for you to reference as you need them, but if it's asking you to prove it with triangles or so forth, that's what it's wanting you to do. Does that make sense? All right.